Hello everyone, I'm Mighty, your hands-on practice assistant. In this session, we'll go through a CFD simulation together step by step and follow along with the practice example. The topic of today's practice example is natural convection thermal flow analysis. What is a natural convection heat transfer analysis? Natural convection is the analysis of fluid flow driven solely by density differences caused by temperature variations without the use of external fans or pumps. Therefore, in this example, a compressible solver is required to account for the buoyancy effect caused by changes in air density. Before we begin today's practice, let's check the model and boundary conditions. The model consists of both solid and fluid domains. The solid domain includes the heat source, heat sink, and PCB. The analysis conditions for each region are shown on the screen. Click New button in the upper left corner to create a project. Now, let's import the model. Click Import in the Geometry tab to open the CAD file. Once the model is loaded, right-click in the workspace and select Hide All Guides. Now, let's move on to defining the material properties and analysis settings. For CFD simulations, fluid and solid material data must be selected from the materials labeled CFD in parentheses. For the air material, select the incompressible ideal gas material model. Next, let's create the material for air, aluminum, pure gold, and PCB. Then, right-click 3D, select CFD 3D, and create the material properties for each of the materials we just defined. Since NFX supports both structural analysis and CFD analysis, it is important to distinguish them carefully and select the correct options. Then, shall we generate the 3D mesh? First, activate only the heat source and heat sink models. Using the Control-C function, set the element size to 0.01 meter. Then generate the 3D mesh as shown on the screen. Click the 3D tab and select the target flow domain. Then, configure the mesh size settings and activate the checkboxes as shown on the screen. After selecting all target regions for mesh generation, make sure that the properties have been correctly assigned. Then, click the arrow on the right and enable Geometry Proximity and avoid Tetra with all boundary nodes to create a higher quality mesh. When generating the mesh, make sure to activate the Match Adjacent Faces and Merge Nodes checkboxes. These options are required to calculate fluid flow and heat transfer properly between each region, so please pay close attention to this step. For the initial mesh generation, it is not necessary to enable the Match Adjacent Face Mesh and Merge Nodes options. However, for all subsequent mesh generations, these two options must be enabled. Please make sure not to overlook this requirement. Now, mesh generation is complete. Let's make sure the mesh is generated well inside the model by using Clipping Plane function. Let's move on to setting the boundary conditions as shown on the screen. Follow along with the boundary condition setup process while watching the screen. Please also check whether the number of selected faces matches what is shown on the screen as you proceed step by step. First, select all bottom surfaces of the air domain and apply the wall boundary condition. Next, select all side and top surfaces of the air domain and apply a pressure boundary condition with a value of 0 pascals. Then, activate only the heat source model and apply a temperature boundary condition of 60 to all of its surfaces. Finally, select the side and bottom surfaces of the PCB and apply a convection boundary condition. Set the ambient temperature to 25 and the heat transfer coefficient to 6. Now, we're almost done. Let's move on to creating and configuring the analysis case. For this natural convection analysis, all analysis modules must be enabled. Click Initial Condition, then select Field Definition, and set the initial temperature of both the fluid and solid domains to 25. If you right-click Analysis Case in the Analysis and Result tree on the left, you can see several predefined analysis types. From here, create a steady-state CFD, then click Edit. You will then see an analysis setup window like the one shown on the screen a moment ago. Configure the remaining settings as shown on the screen. Next, open the Module Data tab and enable Floatability by Density to activate the buoyancy effect caused by density differences. Since natural convection analyses generally require longer computation times, click Fluid Analysis of Analysis tab and increase the number of processors according to your computer's specifications. Because the air material uses the incompressible ideal gas model, the solver type must be set to pressure-based compressible. Before running the simulation, save the NFX file to your preferred location. Then, right-click the analysis case you created and select Solve to start the simulation. This analysis may take some time to complete, so we will skip ahead and review the intermediate results. For accurate results, the analysis should be run for a sufficient amount of time until the solution is fully converged, followed by a detailed review of the results. In the Analysis and Result tree on the left, you can review the results for each calculated step. Click the desired result item to activate the contour display. You can also view vector plots by disabling the contour display in the upper left corner of the Results tab and selecting Slice Plane Vector in Vector tab. Now, let's review the analysis results obtained from the simulation. While following along with today's practice, please make sure to remember these key points. How was today's lecture? Simulation may seem difficult at first, but if you follow the steps and practice hands-on, you can get started with confidence. With MIDAS NFX, learn the fundamentals one step at a time and challenge yourself with a variety of simulation examples. Then, see you again in the next video. This has been Mighty, your hands-on practice assistant.